The ThreadPoolExecutor manages a fixed set of worker threads that execute submitted tasks sequentially from an internal queue. The pool is initialized with a specified thread count, which defines the maximum concurrent task execution capacity. Thread creation occurs synchronously during initialization. Once threads are spawned, they enter an idle wait state, consuming minimal CPU resources while blocking on-queue operations. Task submission is performed via the submit method, which accepts a callable object and optional argument tuples. The method returns immediately with a future object, providing asynchronous access to the task result. The submitted task is appended to an internal queue in FIFO order. The queue implements a bounded size mechanism controlled during executor construction. Worker threads continuously poll the task queue with blocking wait semantics. When a task becomes available, the worker acquires it from the queue and executes the callable within its own thread context. Execution time varies depending on the task's computational complexity. Error handling is performed internally. Exceptions are captured and stored within the associated future object. The future object provides two primary methods for result retrieval: result and done. The result method blocks the calling thread until the task completes and returns the computed value. The done method performs a non-blocking check of completion status. A timeout parameter may be specified on result to establish a maximum wait interval before raising a timeout error exception. Queue saturation behavior is controlled via the queue size parameter. When set to 0, the queue enforces unbounded growth. Positive values establish maximum queue length. When the queue reaches capacity, the submit method will block until space becomes available. This backpressure mechanism prevents memory exhaustion in scenarios with rapidly produced tasks. Thread lifecycle management is handled internally by the executor. Worker threads are daemonic by default, meaning they do not prevent process termination. The thread name prefix parameter allows custom naming conventions for debugging purposes. Thread identifiers are automatically assigned sequential integers appended to the prefix string during creation. The shutdown method initiates graceful termination of the executor. It prevents new task submissions while allowing queued tasks to complete. The method accepts a wait parameter. When true, execution blocks until all tasks finish. When false, the shutdown request is registered asynchronously. Calling submit after shutdown raises a runtime error exception. Context variables are preserved within worker thread execution contexts. Each task executes with access to any context variables set in the parent thread at submission time. This mechanism enables safe propagation of contextual state without explicit parameter passing. Context isolation is enforced. Modifications in one task do not affect other executing tasks. Task ordering guarantees are limited to single-thread executors. In multi-threaded configurations, task execution order is non-deterministic. Completion order may differ from submission order depending on task duration variance. For strict ordering requirements, a ThreadPoolExecutor configured with one worker thread should be employed. Resource limits are established at initialization via the max workers parameter. This setting directly constrains CPU scheduling and memory allocation per executor instance. System-level constraints may further restrict actual concurrent execution. Monitoring tools should be used to verify that thread count matches intended capacity. Exception propagation occurs when result is invoked on a failed future. The original exception object is re-raised in the calling thread's context. The exception traceback reflects the worker thread's execution stack, not the submission context. This mechanism preserves error diagnostics, while enabling error handling at retrieval time. Callback registration is supported via the add-done callback method on future objects. Registered callables execute when the associated task completes, regardless of success or failure. Callbacks are invoked in an arbitrary thread context. They should be written as thread-safe operations. Multiple callbacks may be registered on a single future. Memory management within the executor follows standard Python garbage collection semantics. Completed future objects must be dereferenced to allow cleanup. Large result objects are stored within future instances. Explicit deletion is recommended for memory-critical applications. Queue contents are held in memory until tasks execute. Unbounded queues present memory exhaustion risks. The map method provides a convenience interface for submitting multiple tasks with a single iterable. It returns an iterator yielding results in submission order, applying the timeout parameter globally. Iteration blocks on each result sequentially. This interface is useful for simple bulk operations but offers less flexibility than individual submit calls. Monitoring metrics are not exposed directly through the Executor API. External tools must be employed to measure queue depth, thread utilization, and task throughput. The queue object may be accessed directly for internal inspection, though this bypasses encapsulation. Thread accounting is possible through standard threading module introspection. Finalizer semantics within the context manager protocol automatically invoke shutdown wait equals true upon exit. This pattern ensures resource cleanup without explicit method calls. Entry into the context returns the Executor instance itself for use within the managed block. Exception handling within the block does not affect shutdown behavior. Cleanup proceeds regardless.